catalysis. Now I am going to discuss heterogeneous catalysis. Okay. So let's go. Okay, so can you see the slides?
Yes.
Yes, sir.
Yes, sir.
Okay, so heterogeneous catalysis. So in this, as you know that phases will be different. I will give some example. Maybe you will be able to understand that. So just 1 minute. Okay, so heterogeneous this thing. So there are different phases. For example, so here we are talking about phases of catalyst and phase of reactants. Reactants, this should be different, then that is called heterogeneous catalysis. So there is some examples I will give you so that you understand what do I mean by heterogeneous catalysis. So for example, catalyst can be in liquid phase and reactant can be in gas phase. For example, polymerization of alkenes catalyzed by phosphoric acid. Phosphoric acid. Okay. So reactants are gases, alkenes, right? And then you have a phosphoric acid, which is liquid. So that is one of the example of heterogeneous catalyst. Then solid can be the catalyst, liquid can be the reactants. For example, decomposition of S2O2 on gold. So again, solid here is gold. So catalyst is gold, and which is solid form, and reactant is S2O2, which is in liquid phase. Then you can have solid gas kind of thing, in which catalyst is solid and reactants is gas. For example, ammonia synthesis catalyzed by uh, catalyzed by iron. Okay, and then catalyst can be solid, and then reactants can be gas and liquid. So hydrogenation of nitrobenzene catalyzed by palladium. So there are several different kind of heterogeneous catalysis is possible. In most of the cases, catalyst is in solid phase and reactants are either in liquid or gas phase. Okay, so these are the most common example. This kind of catalysis is quite prevalent in inorganic chemistry or organic chemistry. So it is important to study this because they are industrially important. My focus is on physical chemistry part of it, and certainly Professor Kuntal Manna is going to discuss more about different examples of heterogeneous catalysis which are most commonly used in the industry. Okay, so I will focus mostly of kinetics part. Okay, So the catalysis happen through adsorption, and there are two different kind of adsorption which is possible: physical adsorption and chemical adsorption. The difference between physical and chemical adsorption is given here. So first thing is heat of adsorption. Since in physical adsorption, physisorption, which is known as physisorption, uh, the forces of interactions are van der Waals forces. So heat of adsorption will be smaller. It is between 8 to 24 kilojoule per mole. While in case of chemisorption, it is greater than 100 kilo.
ये दोनों नहीं तो नाम
Sorry, yes, my laptop got discharged. Sorry. Yeah, okay. Can you listen me?
Yes, sir.
Okay, just 1 minute. Okay, so I was talking about Fiji Jobson and Kemi Jobson, and Fiji Jobson, since van der Waals forces are involved, so this heat of adsorption is between 8 to 24 kilojoule per mole. Uh, in chemisorption, covalent bonds are involved, so it is greater than 100 kilojoule per mole. Surface coverage, it doesn't, so heat of adsorption doesn't depend on surface coverage in this, whereas in chemisorption, heat of adsorption depend on. So it is dependence of heat of adsorption on surface coverage. As it is not depending in case of physisorption, and it depends in case of chemisorption. Volume of gas adsorbed to to physical properties. So it is basically dependence of volume of gas adsorbed to physical property. Yes, in physisorption, it is dependent on that. It is dependent on boiling point and critical temperature. Whereas in chemisorption, it is not dependent. Volume of gas adsorbed is not dependent on physical property. Number of adsorbed layer, in physisorption it can be multi-layer, but in case of chemisorption it is unilayer. So these are few things on the basis of which you can differentiate between physisorption and chemisorption. Okay. So now let us see in this again, mechanism of adsorption is very important, and that's what we are going to discuss. So first thing which you need to know is isotherm. What is isotherm? So isotherm is basically adsorption on catalyst as a function of pressure at a given temperature. So this is very important thing, and that's what people look at to understand the mechanism. It is like looking at So one of the most important theory was developed by Langmuir, and this isotherm is known as Langmuir isotherm. So first simplest kind of mechanism which you can think of is unimolecular adsorption. In this, a substrate A adsorbs at surface. Okay, so this is surface. For example, it can be a gold surface, it can be nickel surface. So here we are talking about solid catalyst. Okay, so surface I am going to represent by S. So S, so this is shown as one side. So this is one side on the surface. This A comes and gets adsorbed here, and then your what is known as activation energy gets decreased, and then this S, this A comes out from the surface, giving you a product. So A to P is happening in presence of a catalyst, and catalyst role is simply to decrease the activation energy. Okay. Now, how to look at its kinetics? Okay, so it is shown here, A going to S, and this is your adsorbed basis. So this is, you can think of this as a complex between catalyst and substrate. Okay. Let us think about here. It is quite clearly given that suppose at time initial time, this is the initial concentration of substrate, so A naught. And if you remember that activity of solid is generally given by 1, so it is 1, and then this is 0 at time t is equal to 0. And at time t is equal to t, this is A, which is free A, which has not been adsorbed to surface. and some of the surface sites are occupied, and suppose theta is the fraction of the surface which is covered, then you write 1 minus theta, and then certainly the fraction of the site which is covered will be theta. Okay, so this is the way to write concentration of different term. So this is the first step. The second step is this thing from this A is coming out as a product. Okay, and since concentration of this is theta, so this theta will give you product, and so rate of reaction will be, this is the slowest step, and so this is, if suppose rate constant is K, then rate of reaction will be K into theta. Is this okay? Is it clear?
So, but at T equal to T also, because S is a solid, 1 minus theta should be equal to 1 right? Because it's a solid.
What?
Because S is a solid, so in T equal to T, that concentration term should be 1 only, right?
No, so it is like how much surface it is free. So generally S is shown as a fraction, means fraction. So solid itself is 1. Then some of the sides are occupied. So the free surface will be 1 minus theta. And the combined surface will be, filled surface or surface where A is adsorbed will be theta. Total is going to be 1. Okay. Total is always going to be 1. 1 means complete solid you are talking about. Okay. Is
Okay.
it clear?
Yes, sir.
Okay. So let us see how to calculate this. So what we told that this is 1 minus theta at given time, and this is the concentration of A, this is free A, and this is theta. That's how we represent. And let's take this as a Ka. Again, this is the association constant here. You can think about writing in a dissociation term, but anyway, I am going to use rate constant. So let's take, this is Ka and this is K minus A. Then what I will write? Ka into, at the equilibrium. So what will happen? Ka into 1 minus theta into A is equal to K minus A into theta. K minus A into theta. Or you can simply write Ka by K minus A is equal to concentration of this divided by concentration of this multiplied by concentration of A. So Ka by K minus A is equal to theta divided by 1 minus theta into A. So that's what we write for equilibrium constant, which is here given as Ka. Okay. Here it is association term, but you can, since you can also express in a dissociation term, but generally in the this thing we generally represent this as a association constant. Okay. So K into A is equal to theta by 1 minus theta, 1 by Ka. If I do just uh, 1 by Ka, so you'll get 1 minus theta by theta, and that is giving you 1 by theta minus 1. Okay. So 1 by theta will be equal to 1 by Ka plus 1, and 1 by theta will be equal to Ka plus 1 by K into A. So these few terms are very important, 1 by theta, and which gives you theta term. So theta term is Ka divided by 1 plus Ka. So 1 by theta is this, so theta will be Ka divided by 1 plus K. So theta is, remember, it is fraction of occupied surface. Okay, fraction of occupied surface, and that is given by Ka into 1 plus Ka. If I want to represent this as pressure, then I will write simply this as theta is equal to K Pa divided by 1 plus K into Pa. So depending on whether your substrate is solid, liquid, or gas, you will write this equation. If it is a gas, then I will write theta is equal to K into Pa by 1 plus K into Pa. Okay. So theta is equal to K 1 plus K, 1 minus theta is equal to 1 by 1 plus K. So please keep these two things in mind, because 1 theta gives you fraction of occupied surface, and 1 minus theta gives you fraction of bare surface or unoccupied surface. Okay, so these two terms are important, and this we are talking about unimolecular reaction. And let's see whether you can derive that for a complex thing, because I have already explained you this thing. Okay, so if I so at low a we have discussed this kind of equation quite several times. So theta is equal to k by 1 plus k. At low k this goes out, and so theta is simply proportional to concentration of a, or theta is proportional to pressure of a. So if I plot theta by a, then at initially it will be a first order with respect to a. Okay, at high concentration of a, this cancels out and a cancels out, so it is zero order with respect to a. So theta is simply equal to 1, and that's what you are saying, and so curve will be like this. And rate of reaction, I already told you, that is k, the second step rate constant for the second step multiplied by theta, and so you can simply write k into a 1 plus k a. And this is your adsorption isotherm, theta versus a, or theta versus pressure of a. Okay, depending on whether a is in liquid form or solid form, we can convert this either in concentration term or pressure term. Okay, so this is one case. Now second thing is adsorption with dissociation. Okay, adsorption with dissociation. So first case we discussed is A simply getting adsorbed at the surface. So a unimolecular association, a unimolecular adsorption, you can say. But now what I am going to discuss with you is adsorption with dissociation. For example, hydrogen molecule dissociating into hydrogen atom. So what can be the equation we can write for rate of reaction? Okay, so let us see. Again, A2 with the it will attach to two sides of the surface to give this kind of molecule, and this molecule now getting dissociated and giving you 2A. Okay, so you started with A2, since molecule is A2 naught. This is the initial concentration. This is 1, and this is 0 at time t is equal to 0. But at a given time, you can write A2, or at equilibrium. Let's say at equilibrium. Suppose this is A2. So you can say 1 minus 2 theta, because 2 of the surface site is occupied. So let's write 1 minus 2 theta. You can write simply theta also, it doesn't matter, because in that case theta will be equal to 2 theta, or theta dash you can say, or is equal to theta dash. So I can write 1 minus theta dash. So it doesn't matter, 1 minus theta dash if I write, then this will be theta dash, because this is the fraction which has been occupied by the molecule, occupied by this, occupied, you can simply say occupied. Okay, and now this 2 theta is giving you the product. So what will be the rate constant, rate of reaction? It is simply no. So let us calculate first theta, and then just write. What will be the rate of reaction? Let's see. If this is K2, then you can simply write rate of reaction is equal to K2 into 2 theta square, because 2 of the surface sides are being vacated. So please keep this thing in mind. This is very important. Similarly, when you write this, suppose this is K and this is K minus K minus A. Let's write K minus A, which is the dissociation going from this side to this side. Then I will write K2 Ka into A2. This step is very important. You see, 2 of the sides are taking part in the reaction. It is like A2 plus 2D kind of thing. And what you do? dA square. So in this step is very important. What you have to write is 1 minus 2 theta, which is the concentration per square, because 2 of the sides are getting occupied. Okay, so it is like 2 molecules of some reactants are getting reacted with A2 molecule, one A2 molecule is equal to K minus A 2 theta square, again because two sides are occupied. Okay, two sides are occupied, and K by K minus A is equal to equilibrium constant is equal to 2 theta square by 1 minus 2 theta square into A2. Is this clear here? Why we are taking a square term? This is very important step. Once you know that, it is not difficult to discuss, this heterogeneous or kinetics of heterogeneous reaction. So 1 minus 2 theta square and K minus A 2 theta square. You have to always see how many sides are being used up. Okay. This molecule can also, attach to only one side. In that case, I will not write a square term. Okay. Since this A2 is occupying in this particular case which we are discussing, this A2 molecule is taking two sides on the surface. So it means that A2 is reacting with 2 moles of another reactant. Okay, and that's why we are taking a square term. And so K is equal to 2 theta square by 1 minus 2 theta square into A2. Rate will be, this is the K or K2. If it takes this K, then it is V is equal to K into 2 theta square.
Sir, can this be seen as A plus 2B giving C? The first equation, A2 plus F.
Yeah, A2 plus 2C giving you 2D, something like that. Because again, two sides are occupied here, right? And so 2D, you can say A plus 2C or 2B giving you 2C. Okay?
Yes.
So it is like this. So please keep this thing in mind. This is the only things which you need to keep in mind. After that, it is quite easy. So adsorption with dissociation, and then we will write 2 theta square by 1 minus 2 theta square is equal to K into A2. If I write this 2 theta by 1 minus 2 theta, we will write K half A2 half. And then similarly, I can calculate 1 by, if I divide 1 by, so that I get 1 minus 2 theta by 2 theta, 1 by 2 theta minus 1. So I can get 1 by 2 theta, 1 by theta dash, which is equal to this term. Only difference what you are getting, if you look at this, theta dash is K half, A2 half, K half, A2 half plus 1. So here we have, in place of A2 order 1, it is A2 order half. A2 order half. And if you remember in the kinetics when I was discussing rules to find out the mechanism, when there is a dissociation, then there will be a fraction term will come up, and that's what you are seeing here. Here there is a dissociation of A2. So theta dash is equal to K half A2 half by K half A2 half plus 1. So theta dash versus A2 half. If you plot, you will get like this. It is quite simple. First order when A2 is small, and zero order when A2 is first order. I should not say, because theta dash is half order, we can say, because if I neglect this, it will be half order, and if I neglect 1, then it will be zero order. But since I am plotting theta dash by A2 half, so I will get a straight line. Yeah. Is this okay? Is it clear?
Yes, sir.
Okay. So let us see if you can do this or not. Try for this one yourself. A plus B. So I am taking two reactant. A plus B giving you getting absorbed at S. So this and giving you A plus B giving you product, what you will get. So let me अपने से करो तो थोड़ा सा पता चलेगा. Okay, so what I am writing, A plus B plus surface. So it is reaction between A and B on the surface. What should I get? So this is bimolecular reaction. Okay, so did you try? So let us discuss this. Okay, so we start with A naught, B naught, 1, 0. Okay, then how I will write here? So you see A and B will be are not going to adsorb to same extent. It will depend on equilibrium constant or affinity of A for the surface site and affinity of B for the surface site. So please keep that thing in mind. So what I am going to write, A को अलग से लिख रहे हैं, A naught 1. So suppose A is adsorbed by theta A extent, and I will write 1 minus theta A. Okay. B naught, so 1 minus theta B, but since, so what is the, if you look at the, what is the, you know, free, what is the fraction of side which are free? So that will be 1 minus theta A minus theta B, because theta A is the fraction which is occupied by A, theta B is the fraction which is occupied by B. And so concentration of the free sides will be 1 minus theta A minus theta B. Okay, this is theta A sides is occupied by A and theta B sides is occupied by B. Now, if we are looking at the reaction between A and B, then what I am going to see, it is like, you know, it is simply here. So here it is a kind of reaction between A plus B plus C plus D. Okay, something like that. So it is A, B, this site is theta A concentration, this site is theta B. So it is reaction between theta A and theta B. So what I will write is rate of reaction is equal to K into theta A into theta B. So both sides, because these sides are different, so theta A, theta B लेकर चल रहे हैं. Okay, so 1 minus K into theta A into theta B. So now once we have rate of reaction and we are able to write this, we can know how to. So this is for equilibrium, affinity is K and this is KB, and so I can get theta A and theta B in terms of K and KB. So how I will get that? It is quite simple to do. So we have written this surface side, free surface side is 1 minus theta A and theta B. For A, I am going to write, and this is A, theta A. So K is equal to theta A divided with this whole thing multiplied by A, and KB is equal to again theta B divided by 1 minus theta A minus theta B and into B. So Ka into A is equal to theta A by this whole thing, Kb into B is equal to theta B by 1 minus theta A minus theta B. And so Ka plus Kb if I do, then what I will get is this term, and 1 plus Kb, Ka into A plus Kb into B will give you 1 minus 1 divided by 1 minus theta A minus theta B. Okay, so 1 minus theta A minus theta B is equal to 1 by 1 plus Ka into A, Kb into B. You see here 1 minus theta A minus theta B is equal to simply inverse of this. Okay, so just one. Okay, so theta A into theta B, 1 minus theta A minus theta B is equal to this thing, theta A is equal to this. So K, so theta A is equal to K into A multiplied by this whole thing, and this is equal to 1 by K into A, Kb into B. So that's how you can get theta A. Similarly, theta B क्या होगा? बताओ, थीटा A ये है तो थीटा B क्या होगा?
So KB into A, B upon 1 plus KB into B plus K into A.
So the denominator is going to be same. Only thing is here Kb into B. Okay, so Kb into B. So that's what theta is K into A, 1 plus K into A plus Kb into B. Theta B is Kb into B by 1 plus K into A plus Kb into B. Okay, and then we know that rate of reaction is A into K into theta A into theta B. So your rate of reaction will be K multiplied by Ka Kb A into B divided by 1 plus Ka plus Kb B square. So this is the way you should write about rate of reaction. Is it clear?
Sir, is in this process, is there a way to find out कौन सा पहले attach होगा? Like
कौन सा पहला?
पहले attach होगा surface से A या B, ऐसा भी तो कुछ होता होगा ना?
ये इक्विलिब्रियम की बात कर रहे हैं यहाँ पे. व्हाट वी आर नॉट डिस्कसिंग काइनेटिक्स एज सच, वी आर टॉकिंग अबाउट इक्विलिब्रियम कंसंट्रेशन. So it doesn't matter. Okay. Which is absorbing, because one will certainly absorb fast and another will be low. But here we are talking about equilibrium. Everything is absorbed and reaction absorbed. Then we are talking about this concentration.
Okay.
ठीक है? Any other questions? फिर से मैं करके दिखा दूं? Am I going fast? So let me एक फिर से करके दिखा देता हूं, because so let us see. A is adsorbing to surface, right? To give you so what I told, that initially it is A naught, this is 1 and this is 0. Okay, and at equilibrium let's write A, and suppose theta is the fraction occupied, then theta A, so this is theta A. Okay, now how does B goes? B plus S S. If it is alone, I can write like this, but if it is B, okay, and this is your Ka and this is your Kb. So this is B naught, 1 and 0, and this is B minus 1 minus theta b and theta b. If they are alone, this is okay, but if they are combined, reaction happening parallelly, then fraction of occupied site is not simply 1 minus theta a, because b is also absorbing. Okay. So think about, here I am talking about fraction of vacant site. So occupied site A say theta A है, and occupied site theta B. Occupied site by B is theta B. So what is the vacant site? 1 minus theta A minus theta B. Right? So that's what I am writing here. So once you know that, then you can simply derive it, write in the terms of so let us write this A plus just give me 1 minute time. Okay, so this is A, and what I wrote is this is at equilibrium, it is A, and this is 1 minus theta A minus theta B, and this is theta A. So what will be the K? K will be equal to theta A. This is the product divided by A into 1 minus theta A minus theta B. Hello?
Your future depends on.
Okay, so theta A into theta B. Similarly, I can write for, so let's write this Ka, this is K. Similarly, I can write Kb. Kb is equal to theta B into B into 1 minus theta A minus theta B. Okay, so let's take Ka, 1 plus Ka into A plus Kb into B. If I write, what I will get? So 1 plus Ka into A. Ka into A will be theta A by 1 minus theta A minus theta B, and Kb plus B will be plus theta B by 1 minus theta A minus theta B. And if you take this 1 minus theta A minus theta B, so 1 minus theta A minus theta B plus theta A plus theta B will lift 1. Okay. So if you know that, then I can simply write theta A is equal to, so theta A is equal to, what I will get? Theta A is equal to Ka into A into this quantity. Am I right? And this quantity is equal to inverse of this. Am I right? So theta is equal to Ka into A divided by 1 plus Ka into A plus Kb into B. Kb into B. Okay, and then I can get so theta is equal to Ka into A by 1 plus Ka into A plus Kb into B. And theta B is equal to Kb into B by 1 plus Ka into A plus Kb into B. And rate of reaction is equal to K into theta A. Okay, one thing I just why I'm writing of rate of reaction. Please keep in mind here again I am applying pre-equilibrium concept, and that's why pre-equilibrium concept is very important. So what I am generally saying is this is the fast equilibria. Okay, any case if you take, and this is your slow. Going to this to product is slow. And so I can apply a concept of equilibrium through first step at least. Okay, so equilibrium is established between these three quantities very fast. And so almost you have equilibrium concentration, but then again rate of reaction can be measured. So this is pre-equilibrium concept. So it is not that I am not discussing kinetics. I am discussing kinetics, but I am applying pre-equilibrium concept. Okay. Any questions? Just 1 minute. Give me 1 minute. I don't know. Okay. Any question here?
As if we don't apply pre-equilibrium concept, how will it be different? Like how different will it be?
No, in this case, generally you have to apply pre-equilibrium concept. Again, I tell you that generally the reversible reactions are very fast. Okay. So this is why I am saying that you need to, whatever here we are discussing, we are most of the mechanism which we see in heterogeneous reactions. First step is fast equilibrium followed by the slow step. Okay. But how it will go here again, it can vary, and then rate of reaction as a function of pressure will vary also. Okay. So please keep that thing in mind. There are also possibility which I am going to discuss in the next class that only one gets that job. The other doesn't get that job. One gets a job, then B comes and reacts with this A, giving you product. In that case, rate of reaction will not be like this. All right. For that, again, we can derive rate of reactions. So later on, I will show you that if I see this kind of pressure dependence, what can I think of? What kind of mechanism I propose? But first, I have started with, if this is the mechanism, what can be the pressure dependence? Okay, for example, suppose B adsorbs very high compared to A. Okay, this KAA can be neglected. So what will be the dependence on concentration of A and B? बताओ क्या होना चाहिए? अगर मान लो B is strongly adsorbing, okay, what will be the dependence of rate of reaction on concentration of A and concentration of B?
So A upon B.
A upon B, okay, because this there will be a B square term, and so one B cancels out, but there will be a B in denominator. So what does that mean? That rate of reaction is proportional to concentration of A, but inversely proportional to the concentration of B. Am I right? So when you see that, you understand that you are probably following this kind of mechanism. So first I will derive and then I will discuss one by one few of the mechanism which you come across in when you are dealing with heterogeneous reaction. Is this okay? Any questions?